Welcome back to our OpenFOAM tutorial series. In this lesson, we'll go through the rotating square case which demonstrates how to simulate a rotating body inside a fluid domain using dynamic mesh capabilities. The rotating square case is a classic example of dynamic meshing in OpenFOAM. It is used to study fluid flow around a square object that rotates over time, making it a great case to learn about mesh motion, boundary conditions, and solver control. Okay, so let's go and inside the foam tutorial to find this case. Go inside incompressible, then I will go inside over simply dy foam, and here we will find the rotating square. Okay, so I will copy this rotating square foam. Okay. So then I will find this here. Okay, so it is here. All right, let's open that. All right, so let's go inside system first, system, and here you will find many dicts. Okay, here we are block mesh, we are having control dict as always, decompose par, so it means that we have to run this parallelly. Then here is set fields and here is topo set dict. Okay, so let's go one by one. All right, so let's go inside the block mesh to find like how it has been written. So here is our block mesh. It is written like the normal one. Okay, like normally generally you will find the block mesh dict file in an OpenFOAM case. Okay, so like scaling has been done to 0.01. Okay, so the actual coordinates are this. Okay, and but the domain has to be lower now by 0.01, so it has been multiplied by this one. Okay, so scale down to 0.01. Okay, so multiplied each and every coordinates with 0.01. Then the vertices has been written, all the coordinates have been written of the vertices. Then the blocks have been written. Okay, all right, blocks have been written, and then the boundary names have been given. Okay, boundary names have been given. All right, so here like what is overset, walls, inlet, outlet, hole, front and back. Okay, so here you can find that here it is written background and here it is written moving zone. Okay, so what does this mean? All right, okay, so like background is like it's like fine, it's like the the making of the blocks in the back side, okay, of the domain. So that's why it has been given background. So 25 blocks in x direction, 25 blocks in y direction, and 1 block in z direction. In the second line you will find here it is given as the moving zone. So this moving zone is the rotating or dynamic part of the mesh. Okay, it is defined with the higher resolutions of 16 cells, 24 in x, 24 cells in y, and 1 cell in z. Okay, and again the simple grading has been given which specifies uniform cell distribution. Okay, so by defining these two blocks, one for the stationary background and one for the moving zone, we create a mesh suitable for dynamic motion simulations such as rotating objects or sliding meshes. Okay, all right, so we have seen the block mesh dict. Okay, now let's go to the decompose part. Okay, so decompose part, as I have discussed before in the parallel session. Okay, so the subdomains is given as 3, so it will be using 3 cores of my computer, and here it is defined like this. Okay, so okay, that's fine, we'll go back and then let's go inside the set fields. Okay, set fields dict. Okay, yes, so set fields basically is being used yes, so the set fields is executed to assign initial values to specific regions of the domain. Using the defined cell sets and zone IDs, it initializes velocity, pressure or phase fractions as required by the case setup. Okay, so Alright, so that is the thing which here in the set fields we do. Alright, so let's go back and let's go inside the topo set dict. Okay, yes. So the topo set is used to create and manipulate cell sets, face sets, or point sets. Okay, so you can see here we are using only cell sets. Okay, these sets are crucial for defining regions of interest such as rotating zones or special boundary conditions. So specifically with the topo set is like, like top set. Okay, like we have a specific region in the whole domain where we are considering our our main focus is there. Okay, like the study, the main focus of the study is there where we wanted to have the specific changes of the pressure or the velocity or any other parameter. Okay, that is the thing. All right. Okay, so let's run the command. Okay, let's run the command. All right. Okay, so let's run the commands. Okay, so the first one will be block mesh to make the mesh. All right, let's check the mesh in paraview. I'll go for wireframe, and here is our mesh. Okay, because we have to run other commands regarding the mesh changes only, so we will, what we will do, we will wait. Okay, we will run and then we will analyze it again. Okay, yes, so let's close it and run other commands. So I will clear the terminal, and then I will just run this another command, which is subset mesh box. No, we have to run the topo set. Okay, topo set. So as I've already explained about topo set, so it will manipulate the cell sets, face sets, or point sets according to our according to a region of interest. Okay, so I'll just press enter, and here we are. Then we will run this command sub set mesh box patch hole overwrite. Okay, so what is this? So this subset mesh command is used to extract a portion of the mesh defined by a geometric region, in this case a box. The patch hole option, this one, specifies a new patch for the subset and override updates mesh directly. This override command updates the mesh directly. Okay, so I'll press enter. All right, then again we will run topo set. Okay, this will ensure the correct cell zones which are selected for further processing. So I will go with topo set again. All right, then I will just copy this cp minus r 0.overig to 0. All right, then I will run, finally I will run the set fields. So set fields will be executed to assign initial values to specific regions of the domain. All right, as I've already explained. So I'll press enter, and it has been done. Okay, so now I will go for decompose par for parallel processing. Okay, it is giving some error. Okay, let's run and then we'll analyze. Okay, about that. So we will go for the for this one, for the command. So it will be mpi run minus np 3, then the name of the solver, which is over pimply dy foam. So let me just yes, verb complete dy form, and then I will go for parallel, press enter. Okay, so it is giving error. All right. Okay, so all right, it is giving error, so no, don't worry about that. What we will do, we will use this I've cleaned all the case, and now it is being given this all run dot pre, which has been given by the OpenFOAM. Okay, because sometimes it happens like, you know, some settings which they have done. Okay, so sometimes it doesn't run, because here my agenda of making this lesson was not to give you the full, like the full running. The agenda was to explain specifically about the this set fields, topo set, decompose par, another, and the block mistake. Okay, so we will run with the help of, because only thing is the running of it is required, because error is coming by if you are running the commands, one by one. Okay, so let's not waste the time, and we will just complete it. Okay, so I'll press enter. Okay, all the things have been run. You can see that all the logs have been made. Now I will just go for the all run. Okay, press enter. Okay, it is running. Okay, it is running. So we will go in the next new terminal, and we will press ls. We will go for the rotating square, and here we will go for the log of the solver. Oh, sorry, what I've done, tail minus f log dot. Okay, it has been completed. All right, so it has been completed. So I will clear the terminal, and I will just now I will open the case in para view. Okay, oh, foam.foam file is also not there, and I will make this again. Yes, here we are, and here is our result. Okay, so this is basically our, so let's run it. Let's see like how it is. Okay, so you can see that how the, this is the box which is rotating, so it is like dynamic meshing. Okay, I think, oh, it's really nice. Okay. Mm-hmm. It's perfect. It's amazing. Okay. You know, when you get this type of good results in the CFD, it feels very good. Okay. Okay, I'm pausing it because I want to check for the velocity. Okay, let's go back and let's check for the velocity. All right, let us pause it and let us check from here. You can see that how the mesh is rotating. All right, how the, okay, so what has been done here is like the separate mesh have been made of this, so they are not the part, only they have been made separate, but they are involved connected with both of them, but yeah, they have been involved. So if I'll go to the wireframe, and then here you can see, okay, here you can see, wow, it's amazing. All right, it is amazing. And then it is rotating and we can see the results. Okay, so this is the thing which I wanted to tell you about in this lesson. Okay, so yeah, so this completes the rotating square tutorial. We have learned how to set up and run a dynamic mesh simulation in OpenFOAM and visualize motion effects on flow behavior. In the next lesson we will explore more advanced cases.